Orbits and their intricacies are central to physics and real-life application. There are many aspects of both circular and elliptical orbits that are interesting to investigate and understand. To begin with, we must look into what an orbit actually is. An orbit, as defined by NASA, is a regular repeating path that one object in space takes around another. An object in orbit is called a satellite. We can have natural satellites such as Earth and the Moon, or you can have man-made satellites such as the International Space Station. But regardless of the object, if it is in orbit, it is called a satellite. Now that we've understood what an orbit is, let's look further into it using Keplers Laws of Planetary Motion. The first law states that all planets move about the Sun in elliptical orbits, with the Sun being one of the foci. As the foci move closer together, the orbit more closely resembles a circle. In this way, it can be seen that circular orbits are just an ellipse with zero eccentricity, which results in the foci coinciding, leading to a singular center point. Here we have an example of both an elliptical and circular orbit. So how does an elliptical orbit affect the planet's motion? Well, in an elliptical orbit, there are moments when the planet is closer to the attracting mass or further away. As the planet gets closer, because of the greater attraction, the velocity of the planet substantially increases. The same could be said for the opposite. As the planet gets further away from the Sun, the velocity substantially decreases. In fact, we can take an even closer look at this animation. We can follow the planet in an elliptical motion and look at its velocity vectors. We can see as it's close to the Sun, the velocity vector is extremely high. It is going extremely fast. But as it gets further away from the Sun, the velocity vector shrinks, as does the attraction, showing how if a planet is further away, it moves slower than when it is closer to the Sun. This means, as planets are closer to the Sun, they gain kinetic energy but lose gravitational potential energy, whilst on the other hand, when they are further away, they gain gravitational potential energy but lose kinetic energy. This shows us the total energy of a planet never changes throughout its orbit. In fact, if we look at the previous animation with the circular and elliptical orbits, we can compare the energy at the point of the elliptical orbit where it is the furthest away and the closest to the attracting mass, and see what it consists of. We can see on one side that the gravitational potential energy was very high, but the kinetic energy was low, and we can see on the other side that the opposite holds true. The kinetic energy was very high while the gravitational potential energy was very low. But the total energy in both examples remains same the whole time, holding true to what we've just learned. Kepler's second law, the law of equal areas, states the radial vector joining any planet to the Sun sweeps out equal areas in equal lengths of time. Earlier we mentioned that when a planet is close to the attracting mass, it travels faster, and as it gets further away, it travels slower. This can be seen through the law of equal areas, because despite the eccentricity of the orbit, over the same period of time, a planet will sweep out equal areas. For example, every 31-day month, the Earth sweeps out equal areas. This means that when an object's radius increases, then the velocity decreases. Kepler's third and final law, the law of harmonies, compares the orbital speed and average radius of orbit of a planet. Unlike the last laws, this law makes a comparison against other planets. The law states that the ratio of the squares of the periods to the cubes of their average distances from the Sun, or the average radius, is the same for every one of the planets. In other words, the period squared is proportional to the radius cubed. In fact, let's use some actual data to compare Earth and Mars using Kepler's third law. Here we have two tables. The first table compares Earth and Mars using Kepler's law in seconds and meters, whilst the second table compares Earth and Mars using Kepler's laws in years and astronomical units. In both cases, we see that t squared over r cubed is almost equal for both Earth and Mars. In the first table at 2.977 times 10 to the power of negative 19, and in the second table at 1. In this case, we see how Kepler's laws hold true, and would continue to hold true for any other planets. I would also like to note the Newtonian version of this law. Newton took Kepler's laws and combined it with his knowledge and the law of gravity to explain why this ratio was held true for all planets. He rearranged the formula to get this new one in which r represents the average radius, t represents the orbital period, the capital G represents the gravitational constant, and the capital M represents the mass of the Sun. So as we can see, because it does not relate to any of the planet's mass. It is the same for all planets, and Newton was also able to prove that the centripetal acceleration was all due to the gravity of the Sun. Now that we've learned all this information, let's apply it. First, with orbits around the Earth. There are 3 types of orbits around the Earth: low Earth orbits, medium Earth orbits, and high Earth orbits. The ISS orbits in a low Earth orbit. Anyway, let's discover the velocity required for each orbit and how to theoretically change orbits. Average orbital velocity can be calculated using the formula for angular velocity, which is v is equal to 2 pi r over t, in which r represents average radius and t represents the period of the orbit. Now it's the moment we've all been waiting for. It's time for the math. Let's begin with a low Earth orbit. If there was a satellite in low Earth orbit, its altitude must be below 2,000 kilometers. So let's assume an altitude of about 1,500 kilometers, which would give us a radius of 1,500 plus 6,371, because we must consider it from the center of the Earth, not from the surface. We can also assume it has a period of about 115 minutes. Putting this into the formula, this gives us 2 times pi times 1,500 plus 6,371 all over 115 times 60. This gives an average velocity of about 7.16 kilometers per second. If there was a satellite in mid-Earth orbit, the most common altitude is 20,200 kilometers, which usually yields an orbital period of 12 hours. If we calculated this using velocity, our formula would be 2 times pi times 20,200 plus 6,371, all on 12 times 60 times 60, because in this case we have hours. This would give us an average orbital velocity of 3.9 kilometers per second. In a high Earth orbit, the altitude must be above 35,786 kilometers. In this case, let's take a real satellite's example. One satellite in high Earth orbit has an average altitude of 109,226 kilometers and a period of 6,915 minutes. If we were to put this in our formula, we would get 2 times pi times 109,226 plus 6,371, all on 6,915 times 60. This would give us an average velocity of about 1.75 kilometers per second. Here, I have an animation visualizing a low Earth orbit, medium Earth orbit, and a high Earth orbit. In each case, we can see the velocities have a similar trend. The further away, the lower the velocity, and you can see that in the animation. As we can see with our calculations, the higher the orbit, the lower the speed, which makes sense from what we've previously discussed. Changing from a medium Earth orbit to a low Earth orbit isn't as simple as just changing the satellite's speed. So let's imagine we had a satellite in a perfectly circular medium orbit, and we wanted it to go into a perfectly circular low orbit. What variables are involved? Well, the speed would have to change, but so would the total energy of the satellite. The change in total energy as the satellite goes into a smaller orbit must be negative. The proof of this can be found elsewhere. The work done must also be negative. The only way to make work done negative in this case is to have a force going the opposite direction. Well then, what about the speed? We talked earlier about speed increasing, and this still holds true. The speed increases, but you have to fire the rockets backwards. If speed increases, as does the kinetic energy. This also holds true to what we've learned. The closer you are to the attracting mass, the more kinetic energy. The potential energy decreases for those same reasons. In fact, the potential energy decreases more than the energy needed to orbit, meaning if you just fell into a lower orbit, you'd be going too fast to be in a circular orbit. So we figured out how to change orbits, but this is one of the many ways that Kepler's laws and orbital mechanics can be used to help further space voyage and exploits such as the International Space. So overall, thank you for watching, and I hope you've learned a lot about just how essential orbits are to space voyage and how interesting they can actually be.